Energy is one of those ideas that sounds simple, but it runs almost everything in physics and engineering. In this lesson, we are looking at the first law of thermodynamics. The big idea is this: energy is never created from nothing, and it never just disappears. It moves, it changes form, or it gets stored inside a system. So whenever we draw a boundary around something, our job is to track what crosses that boundary. Energy entering minus energy leaving equals the change in energy stored inside the system. That is the whole story behind the energy balance. Let's build the equation slowly. On the left, we have energy entering the system. That might be heat, work, or energy carried in by mass. Then we subtract the energy leaving the system. Whatever is left must be the change stored inside the system. So the balance is E in minus E out equals delta E system. This is not just a formula to memorize, it is energy bookkeeping. If energy enters, the system's stored energy tends to rise. If energy leaves, the system's stored energy tends to fall. Now, work is not only mechanical. A push on a piston is work, but that is not the only type. Electrical work happens when voltage moves charge through a circuit. Magnetic work happens when a magnetic field acts on magnetic material. Polarization work happens when an electric field shifts positive and negative charges inside a material. The same pattern still holds. Work is a force-like effect, multiplied by a displacement-like effect. So even when it is not a simple push or pull, we can still count it as energy crossing a boundary. Now look at the falling rock. At the top, the rock has gravitational potential energy because it is high up. As it falls, that potential energy decreases. But the energy does not vanish. It becomes kinetic energy because the rock is moving faster. So the gain in kinetic energy is equal to the loss in gravitational potential energy. In words, Ke2 minus Ke1 equals Pe1 minus Pe2. That is why the total energy is still accounted for. The form changes, but the energy is not lost. Inside a system, different kinds of energy can change. Internal energy is the energy stored at the molecular level. Kinetic energy is energy due to the motion of the whole object. Potential energy is energy due to height or position. So for a simple compressible system, we often write delta E equals delta U plus delta Ke plus delta Pe. But many thermodynamic systems are stationary. A tank sitting on a desk is not speeding up, and it is not changing height. So delta Ke is 0, and delta Pe is 0. That leaves delta E equals delta U. For many problems, internal energy is the main thing changing. Now let's look at a control volume. A control volume is just a region we choose to study. Energy can cross the boundary in three main ways. First, heat transfer. Heat crosses because of a temperature difference. Second, work transfer. Work crosses when something like a shaft, fan, piston, or electrical wire transfers energy. Third, mass flow. Mass carries energy with it. So mass entering brings energy in, and mass leaving takes energy out. We build the full balance one part at a time. Start with the heat part. Delta E system equals Q in minus Q out. Then add the work part, plus W in minus W out. Then add the mass flow part, plus E mass in minus E mass out. That is the full boundary balance. Here are two quick heat transfer examples. For the potato, heat enters through the boundary. If 5 kilojoules of heat enters and nothing important leaves, the energy stored in the potato increases by 5 kilojoules. For the pan of water, heat enters from the heater, but some heat also escapes to the surroundings. So the net gain is 15 kilojoules in, minus 3 kilojoules out. That leaves 12 kilojoules stored in the water. This is why the direction matters. in and out must be tracked separately. Now we simplify carefully. We only simplify when the diagram allows it. If a system is adiabatic, there is no heat transfer. That means Q equals 0. If the system is closed, no mass crosses the boundary, so the mass flow energy is 0. And if there is no work interaction, W is 0. For many stationary closed systems, the balance becomes Q in minus Q out plus W in minus W out equals delta U. That is a very common thermodynamics setup. The same energy balance can be written in different forms. If we are dealing with total energy amounts, we use E in minus E out equals delta E system. If we are dealing with energy per second, we use the rate form. That is where the dot notation appears. A dotted E means energy per second. A dotted Q means heat transfer per second. A dotted W means work per second, which is power. If rates are constant, we can multiply the rate by the time. So Q equals Q dot times delta T, and W equals W dot times delta T. The form changes, but the idea stays the same. Energy in minus energy out equals energy stored. Now look at the piston and the graph together. When work is done on the piston, the gas is compressed. The volume decreases. If no heat leaves during that compression, Q equals 0. So the work input increases the internal energy of the gas. That means the gas heats up. Then heat is added from the bottom. Heat enters the system, the gas expands, and pushes the piston back up. That gives work output. The graph shows the state moving around a loop. When the system returns to its starting state, it has completed a cycle. Over a full cycle, the system ends where it began. So the net stored energy change over the cycle is 0. Now for example 1, the rigid tank. The tank is closed, so no mass crosses the boundary. The tank is rigid, so there is no moving boundary work. The tank is also stationary, so kinetic and potential energy changes are 0. That means we focus on internal energy. Shaft work enters through the paddle wheel. Heat leaves the tank. So the balance is shaft work in minus heat out equals delta U. Now substitute the values. 100 kilojoules minus 500 kilojoules equals U2 minus 800 kilojoules. The tank loses 400 kilojoules overall, so U2 equals 400 kilojoules. Now for example 2, the fan speed claim. The fan receives 20 watts of electrical power. Air leaves the fan with kinetic energy. The claim is that the air leaves at 8 meters per second. To test that, we use the best possible case first. Assume no losses at all. That means every bit of electrical power becomes kinetic energy of the air. So W dot electrical in equals M dot times V out squared divided by 2. Rearranging gives the maximum possible speed. Substituting 20 joules per second and 1 kilogram per second gives 6.3 meters per second. So 8 meters per second is too high. Even in the perfect case, there is not enough energy coming in. Now for example 3, the fan heating a room. At first, imagine no heat escapes the room. That means the room is adiabatic. So Q equals 0. The fan still uses electrical power. That electrical energy becomes motor heating, shaft motion, air motion, and finally, thermal energy. So the internal energy of the room increases. Now, if the room reaches steady state, its temperature stops rising. At that point, the heat leaving the room matches the electrical power entering through the fan. So Q dot out equals W dot electrical in. The heat loss is modeled as U times A times Ti minus To. Now substitute the values. 200 watts equals 6 times 30 times Ti minus 25. Solving gives Ti equals 26.1 degrees Celsius. So a fan does not cool a closed room overall. it eventually adds heat to it. Now for example 4, classroom lighting. There are 30 lamps and each lamp uses 80 watts. So the total power is 30 times 80 watts. That is 2,400 watts, or 2.4 kilowatts. The lights are used for 12 hours per day for 250 days per year. That gives 3,000 hours per year. Energy used equals power times time. So 2.4 kilowatts times 3,000 hours gives 7,200 kilowatt hours per year. At 11 cents per kilowatt hour, the annual cost is $792. There is another important idea here. The light energy is eventually absorbed by walls, desks, floors, and people. Once absorbed, it becomes thermal energy in the room. So, lighting reduces the heating needed in winter, but increases the air conditioning load in summer. Now, let's finish by watching how boundary transfers change internal energy. If more energy enters than leaves, internal energy goes up. If more energy leaves than enters, internal energy goes down. More heat in than work out means U increases. More work out than heat in means U decreases. More heat in than heat out means U increases. More heat out than heat in means U decreases. The same idea works for work. More work in than work out increases internal energy. More work out than work in decreases internal energy. And mass behaves the same way. Mass entering brings energy with it. Mass leaving takes energy away. So the full internal energy balance is delta U equals Q in minus Q out plus W in minus W out plus E mass in minus E mass out. The signs are not random. They are just telling us what crosses in, what crosses out, and what remains stored inside. So the first law is really one powerful habit. Draw the boundary. Label what enters. Label what leaves. Then ask what changes inside. Energy is never missing. It is transferred, transformed, or stored. That is the first law of thermodynamics.